In the name of God, welcome to the sediment transport simulation using HEC-RAS 1B course. In this course, I'm going to learn you all about sediment transport modeling in HEC-RAS, and after this course, you can model and simulate each case study about sediment transport modeling. Okay, you know that HEC-RAS is a one-dimensional and most applied model in river engineering studies, and most of the engineers use this model for sediment transport issues. HEC-RAS requires different files for simulation of sediment transport, including geometry. In this course, we are focused only on 1D sediment transport modeling, not 2D modeling. Okay, as I mentioned, HEC-RAS requires geometric files. For 1D case, we need cross-sections defining the geometry of a research study, a file flow, quasi or unsteady flow hydrograph, and in the next step I explain more about these flow hydrographs. And finally, you should set or define a sediment file data, including bed gradation through the rivers, transport function, fall velocity, sorting method, and boundary condition for better simulation of this sediment transport modeling. And finally, you need to create a plan for compare the results of different boundary conditions or transport functions. Okay, defining flow data is one of the most important issues in this model. Now HEC-RAS consider two different flow types. For example, HEC-RAS can simulate a sediment transport with quasi-unsteady flow data or unsteady flow data. Okay, let me zoom in. You know, HEC-RAS allows users to run quasi or unsteady flow hydrograph, and each of them has some benefits and some drawbacks. For example, quasi-unsteady hydrograph model simulates the flow series with a sequence of steady flow computations, as you can see in this figure. Selecting the appropriate hydrodynamic model for HEC-RAS sediment transport analysis involves a classic trade-off between precision and effort. Quasi-unsteady modeling tends to be easier, but because it doesn't or it can't consider or it does not consider flow. It can introduce unacceptable errors, particularly in systems with significant storage and several reaches. As you can see in a quasi-unsteady flow hydrograph, each flow or each the flow hydrograph is divided into different time span, and in each time span, the model assumes that the value of flow is equal to a constant flow. And using a computational increment, the model starts to simulation. In the next steps, I will discuss all about the importance of computation increment and flow duration. This is the structure of a quasi-unsteady flow hydrograph. Contrary, unsteady flow hydrograph requires careful and skillful practice because the solution can be unstable with fixed bed. And also, moving unsteady model cross-section can make stability problem worse because the bed change can introduce instability. However, unsteady flow conserves mass and accounts explicitly for volume change, making it applicable for reservoir modeling, modeling with lateral structure flows, reserve flows, or engineering problems where hydrograph timing is critical. As an overall, in table 1, I want to compare these two different flow hydrographs. For example, quasi-unsteady solves the steady flow backwater equations or a series of flows with associated times or a histogram. While in unsteady flow hydrograph, the model solves the sediment equation implicitly. In quasi-unsteady, model does not conserve flow or account for storage, while in unsteady conditions, the model conserves flows and accounts for reservoir storage. And in quasi-unsteady, the model is lead to more stability output, while in unsteady, the model starts to instability and we face with less stability, and they change and exacerbate the unsteady model instability is common to the sediment solution. Also, in quasi-unsteady, individual time steps take longer, but the variable time step further usually translates into shorter model runs. While in unsteady, flow engine is faster than steady flow, so each unsteady computation is faster, but the unsteady hydro usually requires a smaller time step for stability, which makes run times longer. And finally, quasi-unsteady limits to steady flow options, while unsteady complex we can use complex flow boundary conditions and rules, lateral structures, internal boundary conditions, control gate, pump, and others. While in quasi-unsteady, we can't consider these situations or structures. Okay, the first step for sediment transport after defining flow hydrograph is defining boundary conditions. Okay, let me open HEC-RAS. I will use the 6.1 version, and in this window you can access to flow hydrograph and sediment data parts. In this section you can use quasi-unsteady or unsteady flow data. For example, when I select the quasi-unsteady, you can see the quasi-unsteady data editor will appear. For upstream boundary condition, in quasi-unsteady you can only use flow series as an input boundary condition, while in unsteady state you can use stage hydrograph, flow hydrograph, or stage flow hydrograph simultaneously. Okay, when you select this option, the other options is inactive, and you can access these conditions in unsteady data editor. Okay, as I mentioned, HEC-RAS requires external upstream and downstream boundary condition to run sediment analysis. The quasi-unsteady flow editor automatically includes entire for external boundary conditions. For cross sections require boundary conditions, as shown in Figure 3, and as I showed you previously. When you select the upstream cross sections, the model automatically select these reverse station for external boundary conditions. For upper boundary conditions, you can use flow series in quasi-unsteady data editor. In quasi-unsteady editor, only a flow series can be selected. And for downstream, you can use normal depths. Let me open again. In downstream, you can use normal depths, stage series, and rating curves for boundary conditions. And in the next steps, I will explain more about the performance of and applicability of these boundary condition types. Okay, for flow series, you should enter the data as this format. daily, monthly, and yearly. In the first part, you should select or enter the start date, start time of your simulation. For example, in this picture, you can see the 1st of August 1985 is the first of our time simulation. And in quasi-unsteady, you have 3 important columns: flow duration, computation increment, and flow. Okay, you know flow is the value of flow in specific time step. Flow duration is the time span of that flow. For example, for flow of 3 cubic feet per second, the flow duration is about 100 hours. And the second column is the computation increment. Okay, let me explain more about these columns, especially flow duration and computation increments. Flow duration, the flow duration is constant flow input increment. It does not control the model, or the model, time step. For example, computation increment. For example, if the data are from a daily flow gauge, the duration would be 24 hours, regardless of the computation time step applied to the sediment model. However, the time step cannot be larger than the flow duration. In order to use coarse or coarse time steps, often used during low flow, low transport seasons, flow duration should be large enough to span the entire time step. As an overall conclusion, the flow series editor defaults to 100 rows. Almost all sediment studies require more flow records, and you can press a number of ordinates to increase the flow series lengths up to 40,000 flows. In this window, I click on flow series and go to the flow series editor, and you can see the default version is contain only 100 rows, and you can select on number ordinates and enter the desired value, and HEC-RAS create different or several rows for your sediment data, and you can enter your specific data sets for flow computation increments and flow duration. Okay, computational increment, subdivides the flow duration in different parts. The quasi-unsteady computes new steady flow profile at each computational increment, applying the hydraulic parameter over this time step. This approach assumes bed geometry does not change enough between computational increments to alter hydrodynamic appreciably. Sediment transport is highly nonlinear. Most, transport and bed change is concentrated in relatively brief periods of high flow, and flood events are often highly dynamic. Large quasi-unsteady time steps, for example, if you use 44 hours or more, are often sufficient for low flow periods with little bit change, while moderate to high flows can change channel geometry quickly. Therefore, moderate to high flows require smaller computation time step. Okay, as an overall, for low flow conditions, you can use smaller, larger time step or increment time steps, and for higher flows like flood events, you should use smaller computational increment. Note number 1 says that model stability is very sensitive to computational increment, not to flow duration. if simulation window reports a model fills with sediment, when the model fails, the competition increment associated with that flow duration is probably too large. This is one of the important reasons of model error or warnings. If you see this error in model simulation, you should change the computational increment values. And not to say that computational increments derive runtimes and model stability. For smaller computational increments, the model starts to increase runtime, recomputing geometry and hydraulics. Twin frequency is the most common source of model stability, and you should balance between the smaller and larger and the runtime of model. As you can see in this window, you should enter flow duration is higher than competition increment. For example, if your flow duration is about 100 hours, you can set 24 hours for increment, and model starts to simulate bed change and hydraulic parameters each 24 hours. And you can see when the value of flow is higher, the competition increment must be a smaller value. You can enter desired value for each row, or you can check this competition increment based on flow and enter a range for CI or competition increment. For example, in this figure you can see we can use for values between 0 and 50 cubic feet per second. Competition increment can be used as 24 hours, while for higher flow values you can use a smaller computational increment. And in this example we use 1 hour for a computational increment for higher values. And you can create like this table and model, and you don't need to enter this column, and model automatically use this table, and when the flow falls in each range, the suitable CI or computational increment value will be selected. Okay, this is the new options for defining a computational increment for flow, and you can, and this is very applicable for a large case study and long-term simulations. Okay, the next steps is to set the downstream boundary condition. As I mentioned, in a quasi-unsteady, you can use normal depths, stage series, and rating curve for downstream boundary conditions. Stage time series is very similar to flow hydrographs, flow time series, and it requires a stage duration and a stage value. And in this part, we don't need to enter computational increment, because computational increments for this boundary condition is set as flow series computational increment. Okay, these values for flow duration can be set as flow series flow duration column. And you can that rating curve is the relationship between stage and flow, computing downstream boundary conditions, stage in response to the simulation flow series. And the stage time series is usually the best option for historical analysis. Okay, in this figure you can see the curve that represents the relationship between stage and flow values. And finally, the normal depths. the final downstream option is normal depths, and the normal depths launch a simple window representing a single parameter, I mean the friction slope. The friction slope, or SF in Manning equations, is the slope of energy grid line, and it can be estimated by measuring the slope of the bed. The slope, with this friction slope, the flow, the end value, and the cross-section shape is specified. HEC-RAS can back calculate the stage from Manning equation. As an overall, for using normal depths, you should consider these tips. Normal depth is a popular condition in steady and unsteady flow condition because it requires so little data. However, you should be aware of that. It's also introduced more uncertainty than the stage series or rating curves. However, normal depths should be used with caution. The tips, the second tips is about quasi-unsteady flow data. Quasi-unsteady flow does not flow through the reservoir or gates. I mean that if you want to simulate sediment transport in through the gates or in reservoir, you should run the model in unsteady condition, not in quasi-unsteady. Because if you want to model sediment transport in reservoir, the model fails and give warnings about this issue, and you should change the flow data as flow data to unsteady condition. And finally, instead, it simply completes the backwater stage for each time step based on the flow through the gates, leading to unrealistic reservoir stage fluctuation. Quasi-unsteady gate operations are not recommended for most applications. Consider running reservoir models in unsteady flow conditions. Okay, after defining these items in quasi-unsteady data editor or unsteady data editor, you should set temperature, because in HEC-RAS some transport function requires the temperature data to calculate the transport or sediment values. Therefore, we should enter the values of temperatures as similar to flow series and stage series. If you click on this tab, again you can see editor will be appear that requires temperature value and duration of that temperature, and this column can be used as that columns in flow series and stage series. Let me show again. Okay, you can see that this columns and this value is like to stage series and flow series, and you can select Control and C, and then paste the results. And unfortunately, in HEC-RAS version, you can't right click and select all the data, and you should select Control and click button in your keyboard. Okay, after defining this flow related or time series, you should define the sediment data. Sediment data defining the transport function, defining the fall velocity method, and other related settings. Okay, for entering or editing or defining sediment data, HEC-RAS has a button with the name of View Inter Sediment Boundary Conditions. And when you click on this button, the sediment data editor will be appear. And you can see this editor contains different tabs and different parts for transfer function, sorting method, valve velocity. Before selecting or setting these functions or these items, you should be aware of the applicability and the technical reference of this formula. Okay, the sediment transport has approximately 3 main tabs. However, in this editor, you can see that the first tab is initial condition and transport parameters. The second one is boundary condition. The third one is HEC-RAS bank stability. This is new tab in the newly version of HEC-RAS, and the 2D bed gradation, which is required for 2D sediment transport modeling. And in this course, we don't want to focus on these tabs. We should only focus on these and boundary condition tabs. Okay, the initial condition and transport function is the main or the most important parts of sediment data editor parts. The most important part is the transport function. HEC-RAS contains about 8 transport one-dimensional functions. Let me show you. As you can see, the transport function including HydroAi, England-Hansen, Larsen, Meyer-Peter-Muller, Tufaletti, Meyer-Peter-Muller, Tufaletti, Young, and Wilcock-Crew. Each of them has the advantages and drawbacks, and you should be aware of the applicability and the structure of each formula, and then select the suitable transport function for your case study. And I try my best to show you how can we select best transport function for a case study. Okay, I want to finish this part of this course at this time, and in the next part or in the next video I will show all about these settings and this formula. For the next part, see you soon. Goodbye.